Hi, I'm Jonathan Oxer, and this is SuperHouse. Some years ago, out of the blue, I got a really bad sinus infection. I ended up in hospital delirious for 5 days on an IV antibiotic drip, and it really messed me up. In fact, it's left the sinuses in the left side of my face really sensitive, so now whenever I'm exposed to things like dust or pollen in the air, I can get a really bad sinus infection, and it happens very quickly. So the result is that I've become really conscious of trying to make sure that my environment is clean. I keep this lab as clean as possible. I've got 2 vacuum cleaners in here and I'm constantly vacuuming. I don't let any of the pets in because I don't want any pet hair and that sort of thing in here. I want this to be a place where I can come and actually have nice clean air and not worry about it affecting my sinuses. And because of all the bushfires in Australia recently, there's been a lot of smoke around, and a lot of people have been really concerned about particulate matter in the air. You've probably seen comment about things like PM 2.5 face masks. What I wanted to do was investigate how much dust is in the air, and also things like emissions from 3D printers. People worry about fumes from 3D printers, but from what I've heard, the fumes aren't really so much of a problem as things like tiny particles of plastic which can be emitted and end up floating around in the air as very fine dust, and that can affect people's sinuses as well. So I found some sensors, and I've made a couple of air quality sensors. I'm working on one which is like the Rolls-Royce version at the moment. It's got a colour LCD on the front, and it measures both particulate matter at different sizes and also temperature, pressure, humidity and volatile organic compounds. I'm going to talk about that one in a future video because this is a much more complicated system. But if you want to build something yourself, you can do it very easily just using a couple of parts. All you need is a particulate matter sensor, something like a Wemos D1 Mini with an ESP8266 on it, so it's got Wi-Fi and we can program it using the Arduino IDE, nice and easy. A case to put it in. You really only need to solder a few connections, load the firmware, and you can make yourself your own little particulate matter sensor that will give you some sense of the quality of the air around you. Now the key to this project is this little sensor. It's called a particulate matter sensor. It's made by a Shenzhen-based company called Panteng, which I think translates to like rising vine or something, but it's translated in English as Plantower. And they've made a few different models over the years. They started off with the PMS 1003 a few years ago, and then they've come out with a whole series of sensors since then, which are basically refinements on the same basic principle. What I've got here is a PMS 3003, there's a 5003, and this is a 7003, which is their newest one, which hasn't been out all that long. The 5003 is pretty commonly available, and it comes with a lead that makes it easy to connect, so this is probably the best one to use for this project. The difference between the 3, the 5 and the 7 is really just that they've optimized the mechanicals a bit. The airflow has been improved a little bit, and they've made the 7 quite a bit smaller than the 5. We're going to be using this one for now. Now, the way these things work is quite interesting. What they're trying to do is detect particles floating around in the air that are so small that you can't see them with the human eye. You normally need something like an electron microscope to be able to detect something down in the 2.5 micro region. It's like a 3% of the width of a human hair sort of size, very, very small. In fact, particles of these size are so small that they almost behave like a gas, even though they are a solid. So when they're floating around in the air, they can be distributed for a very long time. They don't settle very easily like heavier dust does. They're so fine that once they go into your body, they can end up in your bloodstream and cause all sorts of problems. So detecting them is quite tricky, and these do it in a very interesting way. What they do is use a principle where a laser produces a beam which is then scattered by the particles, and it's detected by a sensor on the opposite side of a chamber. Now you might see that diagram and think, I remember high school physics, I know what's going on here. Angle of incidence equals angle of reflection, yada yada yada, the light bounces around. But you'd be wrong. It's actually much more interesting than that. When you take any material and you shave it down to being in the order of a couple of microns in thickness, it's no longer totally opaque to light. Light is going to pass through it to some extent. That means that the little particles that are floating around don't just bounce light off them, they can also act as lenses because you have internal refraction taking place within the object. But it gets even weirder than that, because the wavelength of light is somewhere around the 0.5 micron range. So what we're talking about is detecting objects that are so small that they are in the region of the wavelength of light itself. And when you have light interacting with an object which is as small as its own wavelength, it doesn't really behave like a particle anymore. It starts to behave like a wave. And so its characteristics become quite different. You find that the light itself can bend around the back of an object and it interacts with the surface of it in interesting ways. There is a really cool paper which explains how this works. And I'll put a link to it on the project page just down below, so make sure you check that out. It's not all that long and it goes into the background of how light interacts with these particles down at this sort of size. Very interesting if you want to learn more about it. We don't need to understand all of that though, because amazingly this little $15 device implements the laser and the scattering sensor and the control chip which interprets it all and figures out the numbers and gives it to us. The fact that they can do this for $15 just boggles my mind. These things are magic. But because particles exist along a whole range of sizes, they're not exactly 2.5 microns or 1 micron or whatever. What they do is a statistical process called binning, and it categorizes particles into particular size ranges. The number that it gives for PM 1.0, for example, is particles smaller than 1 micron in size. And then the PM 2.5 value is particles between 1 micron and 2.5 microns. PM10 is particles between 2.5 and 10 microns. So the numbers that come out of particulate matter sensors are either a count of the number of particles that it's detected at a certain size range, or the total mass in micrograms per cubic meter of particles in that size range that are detected in the air sample. I think that's plenty of theory for now. Let's just get on with it. Say, Alexa, turn on the soldering iron.
Okay.
And build this thing. So, the parts that we need, we're going to use a PMS 5003 particulate matter sensor. I recommend this one in particular because it's the second most recent version. It's easily available and it comes with a cable that makes it very easy to make connections. We also need a Wemos D1 Mini. Just the basic version will do. It's got an ESP8266 on it. It gives us Wi-Fi and USB. The PMS 5003 has a connector on the side for power and I/O. One thing to be careful of is that it needs 5 volts power, but all of the I/O is only 3.3 volts. The reason it needs 5 volts is there's a fan in it which keeps air circulating through the test chamber. Now there are multiple models of the 5003, including a version that has I2C, but by far the most common is just the basic model which has a UART interface. For a really simple project like this, we don't need to send any data to it. In fact, we don't even need to control the device at all. So we only care about 3 connections. We just want to supply 5 volts and ground to it for power, and then we need to connect to the TX line, which is how the sensor sends its data out. We don't even need to connect to the RX line because we're not sending any communications to the sensor. We're just going to watch it and see what information it sends out to us. Start by plugging the cable in. Make sure you get the connector around the right way, it's slightly delicate, and make sure it's all clipped in properly. Then we need to cut the cable off about 2/3 of the way along, right about here. So as we've just seen, we only care about 3 of the connections on here. So I'm just going to grab some wire strippers and strip off the wires that go to pins 1, 2 and 5. So that's 5 volts, ground and TX from the sensor. And I'll tin those wires so that we can connect them to the D1 Mini. So now we need to find the right pins on the Wemos D1 Mini for making our connections. Now if you have it oriented the usual way, so reset button down on the bottom left here and the USB pin towards you, there is 5 volts ground, and we're going to use D4 to connect to the TX that comes from the PMS 5003. What I'm going to do is bring those connections in from the side that has the USB socket. That's just because I want it to fit into a little 3D printed case that I'll show you in a moment. And just because of the way it's oriented, it makes it easier if the connections come in from that side. So now I've just got to get the pin 1 from the PMS going into the 5-volt connection on here, and I'll solder these in place. Put on the 5 volts to start with. Then pin 2 is the ground from the PMS, so I'll solder that in place. And then pin 5, TX data coming out of the PMS, going into D4 on the D1 Mini. Oop, it's flopping around a little bit there. I've just got to try to make that stay in the right position. I'm trying to do this in a way that is visible to the camera, which is not very convenient. Okay, and that's it. So if we look at the pin out as a diagram, you'll see that it's actually incredibly simple. It's just these 3 soldered connections, and if we look at this now oriented the way I had it in that picture, so D1 Mini kind of upside down, you can see 5 volt ground and pin 5 TX coming from there. And believe it or not, that is the total of the electronics assembly. We can now plug this into USB and get some software onto it and get some data out of this. So this is pretty much the easiest assembly project that you'll ever have to do. For software to go on this sensor, you have a few options. I'm going to show you 2 different options. And the first is definitely the easiest. If you just want something that will get you up and going quickly, go for Tasmota. You might think of it as being something that you use on a device like a Sonoff for remote power control, but because Tasmota has the built-in infrastructure for working with sensors, it has support for the PMS 5003, and also it has easy Wi-Fi setup, all of those good things, MQTT. It's perfect for this project. The easiest way to install Tasmota on this device is to use the Tasmotizer. I've just done a whole video about this, explaining how to install it and set it up. It's pretty easy, so I won't repeat it here. Once you've got Tasmotizer running, click refresh and have a look at what ports you've got here. And then what I'm going to do is take the device, plug it into my USB hub, and we can click refresh. And now we can see that we've got a new device in here. It's doubled up. There's a TTY.USB serial and a CU.USB serial. I'm going to select CU.USB serial. This is the air quality sensor. And I'm also going to install a release version of Tasmota. So I'll click on release, and we want tasmota.bin, just the standard installation, and click on Tasmotize. So what this does is pull down the latest version of Tasmota, and it uploads it onto the D1 Mini. It takes care of all of it for you. You don't need to mess around with ESP tool. So it's very cool. It takes a minute or so to do the upload, so be patient, just sit there and watch the progress bar. All done. So now we need to power cycle it. I'm just going to unplug the device, plug it back in again, and we'll just say OK in here. Now the D1 Mini will restart and it will be running Tasmota. But it's not on our Wi-Fi network yet. We need to configure it. Once again, Tasmotizer saves us. So come along here and click on Send Config, enable the Wi-Fi section, put in the details for your Wi-Fi network, and down here where we have the option of putting in either a template or a module, normally what you would do is you would select module and then say what type of device it is. But we've built a little custom module here, so what we can do is not use module, we'll use template. I've created a template which pre-configures this, so I'm just going to paste that template in there, and this is available on the SuperHouse site. I've got MQTT set up already. I'm just going to click save, and this will send the configuration to the device. Our device now has Tasmota installed, and it's being configured. If you use that template, it'll already know about the PMS 5003 sensor, and it'll be acquiring data from it. So now what we can do is either look at the MQTT broker to get the data, or we can use the web interface. What I'm going to do is have a look in my DHCP server to find out the IP address that's been assigned to this device, and then open the web interface. Once I've found the IP address for the new device on my network, I just put it into a browser and we get this interface. You can see that it's already giving us values in micrograms per cubic meter at 1, 2.5 and 10 micron sizes, and it's giving us ppd, which is particles per deciliter, and that is giving us in 0.3, 0.51, 2.55 and 10 micron sizes. So these are a count of the number of particles in that particular size range which it's detecting per deciliter. These numbers can be quite interesting because when you have a very clean environment, you might find that the value in micrograms per cubic meter is below 1. So in this case we've got 0 for the 1 micron size, but if we look down here we've got 20, well it's just dropped to 18 ppd, and then at 0.5 we've got 48, and at 0.3 we've got over 100. But because these particles are so small, even though it's counting this number of particles, it's still rounding down to 0 micrograms per cubic meter. And what we can also do is have a look at how this D1 Mini has been configured in Tasmota. We didn't have to do anything because I've already created the template. And if you paste the template in, then you get the pin assignments and everything taken care of for you. But you can also do it manually. Now to see what happened in the template, we can come into the interface and click on Configure Template, and this is what I set up. I just set SuperHouse AQS, or Air Quality Sensor, as the module name. It's based on the generic module. And then GPIO2, which is D4 on the D1 Mini, I set to be PMS 5003. And that enables the driver for that particular sensor, and Tasmota can then process the data that's coming in on that pin and then display it to us. And that's why we're getting these values coming back to us in here. And this is also being reported to MQTT because we configured MQTT in that setup. So we can now link this to our home automation system and chart and report those values if we want to. So now we've got something that's functional, but it's still not pretty. And this is a D1 Mini wired to a sensor. It's kind of ugly. You can't have this sitting on the shelf in your lounge room and not look like some Frankenstein's monster sort of project. So what I've done is designed a 3D printed case that encloses all of this. The case is almost symmetrical. The only difference is that one part of it has holes in here to align with the holes in the sensor. So I'll disconnect power from here. And the way this works is I have the main compartment here for the PMS 5003, and you can see a section down here where the D1 Mini fits in, and then a bit of room for the cables to wrap around. That's why when I cut these leads off, I did it at about 2/3 length. It gives enough room. Now there are no fastenings to keep this enclosure attached, but what I've done is tuned the size so that on my printer at least, this slides in, and it's basically just like a firm slide fit. You can pull it out, no problems, but it's not going to fall off. It stays there by itself. And then what I do is bring the D1 Mini around, and this is also why I said earlier to bring the wires in from the side with the USB socket. That then slides into those little slots and it's held in place, and the USB socket is then visible through this part of the case. So then I can grab a pair of tweezers, do a little bit of jiggling, a bit of stuffing, and just shove these wires down into this part of the case. Make sure everything clears. And there we go. You can see that it's got the sensor and the D1 Mini. And then I can just take the other half of the case, bring it over the top, and slide it together. Now in this case the D1 Mini is kind of getting in the way. You can jiggle it a little bit with a pair of tweezers or something. It's not quite going into the other slot yet. But if I move that, that's it. And it all closes up. So now we've got something that looks much more respectable. I mean, this sort of thing, you can put it up on a shelf somewhere. Where can you see that? I don't know. But that could go up on a shelf in your lounge room or kitchen or wherever, and it just looks like a little Apple device, I think. So then we can plug in power. It powers up. There's no real way to tell at the moment because there's no LED visible, but this is now powered up. You can just see the blue LED flashing under there. and taking samples. So this will now be reporting back to the MQTT broker with the values that it's taking. If you want the simplest possible air quality sensor, this is it. It's the PMS 5003, a D1 Mini, 3 soldered connections, Tasmota, and a 3D printed case. I'll put up the design files for the 3D printed case on the SuperHouse site on the page for this episode. So if you're watching this on YouTube, make sure you look down below for the link in the video description. That takes you to a page with far more information than is included in this video, including photos of the assembly process and links to the software and everything you need. Make sure you check that out. So that's really all you need if you want to build the most basic particulate matter sensor. But there are some big limitations. Firstly, the Plantower sensor that is in this is not really designed for continuous long-term use. The laser and the sensor within it can degrade over time. They're really only rated to about 6,000 continuous hours of use, which works out to be like 8 or 9 months. It's not that long. The usual way to deal with that is to put the sensor to sleep for a few minutes, wake it up, give it time to move air and stabilize, take a reading, and then put it back to sleep again. So in the next episode, what we're going to do is look at a more advanced version of this, which will use fancier software that will take care of that for us. And the other thing is that there's no way to look at this and interact with it directly. It publishes all the information to MQTT or on its web interface. So it would be really handy if you could just walk up to it and look at a display and see what it's reading. Well, it doesn't take many more parts. This is a slightly fancier version. It's very similar to the one we've just done today, except that it adds a display and a mode switch. So you can just walk up to it and see what the reading is directly on the unit. So that is the display model that we're going to look at in the next episode. So come back to check that out, and in the meantime, go and build something cool.